problem 3.29 of Taylor's Classical Mechanics from chapter 3. This is a problem on angular momentum. The situation we have here is a uniform spherical asteroid of radius r0 is spinning with an angular velocity omega naught. And it's saying that it's picking up more matter until its radius is r. And assuming that the density remains the same and that the additional matter was originally at rest relative to the asteroid, so it's not contributing anything extra, find the asteroid's new angular velocity. So we have here that the moment of inertia for the asteroid is 2/5 mr squared for a sphere. And we know through the conservation of angular momentum that the initial moment of inertia times omega is going to be the final moment of inertia times the final angular velocity. So we know these things, and we're given that initially it has the radius r0, and it's going to have the final radius there. So to start out, we need our I0, which is our initial moment of inertia. It's going to be 2/5 mr squared. We want things in terms of the density, which is going to be the volume of a sphere, which is 4/3 pi cubed times the density. That's going to be our initial mass. So we now know that that is equal to 4/3 pi r0 cubed rho times 2/5 r0 squared. So the initial moment of inertia is going to be 8/15 pi r0 to the 5th times rho. That's our initial moment of inertia. For our final moment of inertia, we're going to end up with a similar calculation here. The only difference being that we end up with the r final raised to that 5th power. So knowing that they're going to be equal, we'll take our initial inertia, 8/15 pi r0 to the 5th rho, set that equal to the final. We actually need our omega in here as well, is going to equal the final 15 pi, that final radius raised to the 5th power times rho times the final angular velocity. And as you can see, these are going to divide out nicely. That density is going to divide out, and we're left with r0 to the 5th omega naught is equal to that final radius raised to the 5th power times our final angular velocity. And if we go back to our question, they're asking us to solve for that final angular velocity. So to solve for that, we divide by that final radius, and we end up with r0 to the 5th over r final raised to the 5th power times omega naught equals that final angular velocity, which can also be written as r0 over the final raised to the 5th power times omega naught. Now, for the second part of the question, it's asking us what is the final angular velocity if the radius doubles. So what that means is that our final radius is going to be 2 times our initial radius. So if we try and find out what the final angular velocity when we plug that in, plugging in 2r0 for that final radius raised to the 5th power times the initial angular velocity, you're going to notice these r0s will go away, and you're just going to have the final angular velocity equals 1/2 raised to the 5th power, which is going to equal 1/32. I mean, not. So if the radius doubles, the final angular velocity, to account for the conservation of angular momentum, is going to be 1/32 of what the initial angular velocity is.